Hello everyone, and thank you for being here. We are Group 32, and today we'll be presenting 2HADRAD, a portable life detection radar system. Our system is a battery-powered multimodal search and rescue device that's designed to detect human presence and provide actionable location data in emergency environments.
Shannon Hankinson, Electrical Engineering.
My name is Bailey Hitt, and I'm an electrical engineering student.
My name is Ryan Anderson, and I'm an electrical engineering major.
Hi, I'm Joshua. I'm studying computer engineering.
Search and rescue teams often operate in low visibility or structurally unstable environments. Current tools either focus on a single sensing modality or require bulky infrastructure. 2HADRAD was developed to enhance search and rescue operations by integrating millimeter wave radar for motion, heartbeat, and breathing detection, ultra-wideband for positioning, infrared sensing for thermal confirmation, and inertial and barometric sensing for relative localization. All of this is fused in real time on an ESP32 microcontroller to generate high-confidence detections and estimate 3D locations. When detection thresholds are met, the system provides visual alerts and logs positional data through a mobile interface.
Our primary sensing objective is radar-based human detection at greater than or equal to 2 meters line of sight that establishes minimum viable detection range for open space rescue scenarios. We then confirm presence thermally within 1 meter using IR, which allows us to reduce false positives from non-biological motion. Localization is constrained to within 2 meters using INS and barometric sensing, with an advanced objective of improving outdoor accuracy to 1 meter through GNSS fusion. From a usability standpoint, detection feedback must occur within 5 seconds, and the device must operate continuously for at least 2 hours on battery power. Finally, UWB provides responder to victim distance estimation beyond 3 meters, stabilizing relative spatial awareness in GNSS-denied environments. It's important to note that breathing rate and heart rate detection via the radar is a stretch goal that we hope to be able to achieve, as well as machine learning-aided detection of human life using IR data. This slide formalizes those goals into quantitative subsystem constraints. On the left, we define overall system specifications: radar detection range greater than or equal to 2 meters, fuse detection accuracy greater than or equal to 90%, average system power less than or equal to 10 watts, battery life greater than or equal to 2 hours, and UI response within 5 seconds. On the right, we break those down to component-level requirements. Radar integration latency must remain under 200 milliseconds to support near real-time feedback. The IR subsystem must confirm heat signatures within 1 meter using a properly conditioned I2C or SPI interface. The INS must maintain less than 2 meter drift over short paths, and GNSS fusion improves that to less than or equal to 1 meter outdoors. The MCU must run at 3.3 volts, at least 240 megahertz, and support multiple UART, I2C, and SPI interfaces simultaneously. That requirement directly influenced our ESP32 selection. These constraints collectively shaped our power architecture, interface mapping, and fusion logic implementation.
This diagram shows the overall architecture of our handheld life detection system and how each subsystem interacts. At the top is the sensor subsystem, which includes the inertial navigation system, infrared thermal sensor, ultrasonic safety sensor, and ultra-wideband module. These sensors provide environmental awareness and victim detection inputs. The MM-Wave radar module operates as the primary detection engine. It transmits and receives 60 GHz frequency-modulated continuous wave signals, performs onboard DSP processing, and outputs usable baseband detection data to the MCU. The microcontroller acts as the system coordinator. It performs sensor fusion, processing detection logic, manages communications, and controls the user interface. The power subsystem regulates the lithium-ion battery input into stable 5-volt and 3.3-volt rails to support radar, sensors, and controls. Finally, the user interface subsystem provides real-time feedback through the touchscreen display, navigation controls, audio alerts, and LEDs. This modular architecture allows us to fuse multiple sensing modalities while maintaining power efficiency and system reliability in emergency environments. To keep development organized and allow parallel progress, responsibilities were divided by subsystem and technical specialty. Ryan leads the power subsystem and serves as primary lead for the radar module, ensuring stable power delivery and reliable RF operation. I serve as primary lead for the sensor subsystem, integrating the INS, infrared thermal sensor, ultrasonic safety sensor, and the UWB localization. I also support radar integration to ensure seamless sensor fusion. Josh, our computer engineering lead, is responsible for the MCU firmware, system logic, and mobile application development, enabling wireless communication, data processing, and real-time operator feedback. Bailey leads the user interface, develops operator alerts and display interaction, and is designing the handheld enclosure, ensuring the device is durable, ergonomic, and practical for field use. She also supports the power and sensor subsystems. This structure allows hardware, firmware, and mechanical design and user interaction to be developed in parallel while maintaining tight system integration.
So this is our budget. It's broken down between the radar module and PCB, other PCBs, and the various sensors and peripherals that we've required. The budget's mostly stayed within our expectations, with of course the radar module being pretty costly compared to the other parts. But at this point, all of the PCBs and most of the sensors and peripherals that we need have been ordered, so we don't expect this total to change in the future. So here's a brief overview of the peripherals that we'll be using. For the audio system, we'll have an amplifier and a speaker to provide an additional layer of utility and accessibility to the user. They'll hear beeps or buzzes based off of new human detections, and also just as confirmation as they interact with our interface, such as pressing things on the touchscreen or navigating with the buttons. For heat detection, we'll be using an infrared sensor. This will provide temperature data from the surroundings of the device, and this will help us corroborate with human detection based off of human heat signatures. For location tracking, we'll be using an ultra-wideband sensor, and this functions according to a system of anchors and tags, wherein tags would provide location data in reference to the anchors around it. So the more anchors, the better and more accurate the data will be. For safety, in order to comply with FCC regulations, the radar needs to be 22 to 30 centimeters away from the human in order to prevent any excessive radiation exposure. So in order to accomplish this, we have an ultrasonic sensor for distance detection. Finally, we'll be using an LCD screen as the main user interface for our device. This is where most of the information will be read and most of the interaction will take place.
Ultra-wideband was selected to provide reliable relative positioning when global navigation satellite system is unavailable, particularly indoors or in obstructed environments. UWB determines distance using time of flight measurements, enabling centimeter level ranging accuracy that is significantly more precise than GPS and more reliable indoors. We compared the DWM-1000 and DWM-3000 platforms. While both advertise similar ranging accuracy, the DWM-3000 represents a new generation architecture with several important improvements. The DWM-3000 includes an enhanced RF front end, providing improved receiver sensitivity and better signal integrity in cluttered environments. This improves detection reliability when signals are partially obstructed by walls or debris. It also features improved multipath mitigation, allowing it to better distinguish the direct signal path from reflected signals. This reduces ranging errors in environments with reflective surfaces such as buildings or indoor structures. For rapid development and validation, we are using the DWM-3000 evaluation board during testing, while it will also act as the mobile tag in our final project, allowing us to verify ranging, performance, and communication behavior without requiring fine pitch assembly. We're currently validating the functionality using Qorvo's UWB application tools, which provides real-time ranging visualization and performance verification while we await the final chip. Once the chip arrives, the DWM-3000 chip will be integrated into our custom PCB and will function as the anchor node, enabling full anchor tag system while reducing size, power consumption, and system complexity. In our configuration, one anchor and one mobile tag will provide relative positioning between rescuers and allow victim locations to be logged for situational awareness. To provide orientation, motion awareness, and positioning capability, we evaluated several integrated INS modules. Our comparison focused on sensor fusion capability, dead reckoning performance, power consumption, cost, and suitability for handheld search and rescue deployment. We selected the M5 Stack M135 INS module because it integrates GNSS, a 6-axis IMU, magnetometer, and barometer into a single calibrated unit, providing complete orientation and positioning capability with minimal integration overhead. This solution offers the best balance of capability, power efficiency, cost, and rapid system integration, making it well suited for a compact search and rescue device. For validation, we conducted outdoor testing of the INS GNSS module to verify positioning, performance, and sensor integration. During testing, the system successfully acquired satellite lock and streamed real-time latitude, longitude, and heading data to the ESP32, confirming proper communication and sensor fusion functionality. We observed an average positional offset of approximately 5 meters. This level of accuracy is consistent with standalone GNSS performance and consumer-grade receivers and reflects expected error sources such as satellite geometry, atmospheric delay, and multipath reflections. Moving forward, we will improve accuracy through sensor fusion with the IMU, consider filtering techniques such as the Kalman filtering, and calibrating the magnetometer and heading alignment. This subsystem will also support indoor navigation by leveraging inertial dead reckoning when GNSS signals are unavailable, ensuring continuous positional awareness in obstructed environments. The ultrasonic sensor provides a proximity-based safety interlock to disable the radar when an object enters the 22 to 30 centimeter safety zone, ensuring compliance with FCC RF exposure safety guidelines. We compared ultrasonic ranging to PIR motion sensors and short-range IR proximity sensors. PIR sensors detect motion but cannot measure distance, making them unsuitable for enforcing a precise safety buffer. IR proximity sensors are sensitive to surface reflectivity and lighting conditions. The HC SR04 provides direct distance measurement with consistent accuracy, allowing reliable enforcement of the safety threshold required for regulatory compliance. Because it emits no RF energy, consumes minimal power, and interfaces with only 2 GPIO pins, it offers the simplest and most reliable safety solution. The photo shows our bench validation setup, where the ultrasonic sensor triggers a visual proximity alarm when an object enters the safety zone, confirming reliable detection and immediate operator feedback. To support victim detection in low visibility environments, we integrated a thermal infrared sensor. The MLX 90640 provides a 32 by 24 thermal array, enabling spatial heat mapping while remaining compact, low power, and suitable for embedded processing. By analyzing heat distribution across multiple pixels, the system can distinguish human-sized heat signatures from smaller environmental heat sources, reducing ambiguous detections. We conducted preliminary testing using controlled heat sources to validate detection capability. The thermal image demonstrates how the sensor clearly identifies heat signatures and distinguishes them from cooler surroundings, confirming suitability for victim detection. This slide shows the finalized PCB layout of the sensor subsystem, which integrates the INS module, infrared thermal sensor, ultrasonic safety sensor, and UWB chip. This board is designed as part of a stacked PCB architecture, allowing each system, power, radar, sensors, and user interface to remain modular while still integrating into a compact handheld form factor. To ensure proper sensor performance, several physical placement and mounting considerations were incorporated into the design. The infrared thermal sensor and ultrasonic sensor will be mounted so they have direct exposure outside the enclosure. This allows the thermal array to detect heat signatures without obstruction and ensures the ultrasonic sensor maintains a clear acoustic path for reliable proximity detection. The GNSS antenna associated with the INS will be mounted externally on the enclosure to improve satellite visibility and positioning accuracy, particularly in outdoor search and rescue environments. Although the INS module is mounted on the PCB for integration simplicity, its placement within the stack design is being optimized to minimize interference from the speaker magnet and switching regulators. This helps preserve the magnetometer accuracy and overall inertial performance. The PCBs are connected using screw terminal block connectors, allowing reliable power and signal distribution between boards while supporting rapid assembly, testing, and subsystem replacement. This modular architecture enables parallel development, simplifies troubleshooting, and allows future upgrades without redesigning the entire system.
We evaluated multiple radar modules. The IWR 6843 AOP was selected due to its integrated DSP pipeline, antenna on-package architecture, and embedded vital sign firmware. Unlike lower-level RF front ends, this module integrates the RF chain, ADC hardware accelerator, C674X DSP core, and R4F control core. This architecture reduces external signal processing burden, simplifies PCB RF layout, and enables portable embedded deployment without requiring external computing hardware. The completed schematic on the right and the PCB on the left are of the radar breakout board. The module allows for 3 communication functionalities, such as Bluetooth, PC, and a 60-pin connection. For our purposes, as detailed in the following slides, the 60-pin connection is how we are accessing the data on the module. However, due to manufacturer documentation errors, the current most efficient method to ensure proper functionality under the given time constraints is to bring out all 60 pins from the connector to header pins, and then we'll be able to test each suspected pin for the required UART signals. Electrically, integration is intentionally simple. The radar requires 5 volts and ground. Communication uses 3 UART lines. 2 lines form the CLI interface. The ESP32 transmits configuration commands through CLI RX, and the radar responds with acknowledgements through CLI TX. This interface is only active during configuration or status exchange. The third line streams TLV data continuously at runtime. Separating CLI and data channels prevents command traffic from interfering with streaming throughput and keeps the data path deterministic. This mapping satisfies the MCU interface requirements and preserves clean separation between configuration and sensing operations. The system is powered by a 3-cell lithium-ion pack with an input range of 9 to 12.6 volts. From that source, we derive regulated 5 volt and 3.3 volt rails, each designed to support approximately 1 amp peak current with margin. Because the system must operate continuously for at least 2 hours while remaining thermally stable in a sealed enclosure, linear regulation was not viable due to excessive power dissipation. We therefore implemented buck switching regulators to maintain efficiency above 85% under expected load. Additionally, we isolate high current digital loads from sensitive RF and analog sections. This minimizes switching noise injection into the millimeter wave radar front end and thermal sensor interfaces, which is critical for maintaining signal integrity and detection accuracy. The selected buck regulator, the LM2576, supports up to 3 amps output current, which provides significant headroom above our approximately 1 amp peak requirement per rail. This margin ensures stable operation during transient events such as radar startup or display refresh. It accepts a wide input range covering the full 3S battery envelope without additional pre-regulation. The fixed switching frequency simplifies output filter design and makes ripple behavior predictable. This allowed us to size inductors and capacitors analytically rather than relying on empirical tuning. Measured in datasheet efficiencies in the 85 to 90% range significantly extend battery runtime and reduce internal temperature rise. That directly supports both our 2-hour runtime requirement and enclosure thermal constraints. Finally, the device is mature and widely deployed, reducing integration risk and layout sensitivity during PCB implementation. The power carrier board serves as the central electrical backbone of the system. It receives battery input, routes protection circuitry, hosts both buck regulators, and distributes regulated rails to all subsystems. By physically separating power conversion from the radar and sensor PCBs, we reduce electromagnetic interference coupling into sensitive analog and RF traces. This separation also simplifies grounding strategy by allowing controlled star distribution of power and return paths. Structured connectors distribute 5 volts, 3.3 volts, and ground to each board, improving modularity and allowing subsystems to be tested independently. This architecture improves serviceability, reduces integration risk, and maintains cleaner signal environments for high-frequency sensing. The device uses a 3S18650 lithium-ion battery pack operating between 9 and 12.6 volts. Protection is implemented at multiple levels. At the pack level, we include inline fusing to protect against catastrophic short conditions. A commercial battery management system provides overcharge, over-discharge, overcurrent, and short-circuit protection. Downstream of the BMS, we implement an additional load fuse to protect system electronics from internal faults. This layered protection strategy aligns with lithium-ion safety best practices and relevant standards such as UL 2054 and IEC 62133. The regulated 5V and 3.3V rails then supply the radar module, ESP32, INS, IR sensor, and user interface circuitry. The result is a battery architecture that prioritizes electrical safety, runtime reliability, and field deployable robustness under unpredictable rescue conditions.
The LCD is a critical component of our system because it serves as the primary user interface. All human detection results and the IR heat map visualization are displayed directly on this screen. In addition to the visual output, the display includes touchscreen capability, allowing interactive menu navigation and system state changes directly through the interface. If the screen cannot render information clearly in real time, the user cannot effectively interpret detections in the field. We evaluated several display options before making our final decision, including multiple 4.3-inch TFT modules using drivers such as the RA8875 and the SSD1963. While these offered higher resolution, they introduced trade-offs. Many require higher power consumption, more complex driver configurations, and in some cases, parallel interfaces that would consume a large number of GPIO pins. Given the limited availability of these pins on the ESP32 Room 32E, especially after allocating pins for the radar, IR, and other sensors, a parallel interface was not practical. A higher resolution would also increase memory and processing demands on this microcontroller. We also evaluated the physical size. The 3.2-inch measurement is diagonal, so we verified the actual width and height against our proposed enclosure constraints to ensure proper fit. Originally, we had a weight requirement for this device, and selecting a smaller display supported that goal, even though the weight is no longer a final constraint. Ultimately, we selected the 3.2-inch ILI 9341 TFT LCD with integrated touchscreen capability. It operates at a 240 by 320 resolution, which is sufficient for rendering our IR map without overloading the ESP32. The display communicates via SPI and is directly compatible with 3.3V logic, eliminating the need for level shifting and minimizing GPIO usage. Power consumption was another key factor. This display draws approximately 80 to 120 milliamps, significantly lower than the larger alternatives, an important consideration for our battery-powered system. During prototyping, we validated stable 3.3V operation, reliable SPI communication, accurate touch response, and successful real-time rendering of our heat map output before transitioning this to our PCB integration. Overall, the ILI 9341 provided the best balance of size, efficiency, simplicity, and the interactive capability for our application. The amplifier stage supports the auditory portion of our user interface. While the LCD provides visual confirmation, the audio subsystem delivers immediate feedback for events such as system startup, status changes, or human detection alerts. This ensures the user receives confirmation even without looking at the screen. We evaluated several amplifier options, including analog input devices like the PAM8302 and the LM386. However, these required either an external DAC or additional analog conditioning from the ESP32, which increases the complexity and even potential noise. We ended up selecting the MAX 98357A, a mono Class D digital amplifier with an I2S input. This allows direct communication with the ESP32 Room 32E, eliminating the need for an external DAC and simplifying the signal chain. It operates at a 3.3V logic, delivering up to approximately 3 watts of output power and offers high efficiency, which is important for our battery-powered system. Adafruit provided well-documented ESP32-compatible I2S libraries for this device, which allowed us to quickly prototype and validate audio output during our demo phase. After confirming functionality on a breadboard, we transitioned to integrating the MAX 98357A directly onto our custom PCB to optimize routing, reduce wire complexity. We paired it with a 4-ohm, 3-watt full-range speaker rated appropriately for this amplifier's output. Overall, this provides a clean, efficient, and fully digital audio subsystem that complements our visual interface. This button serves as a secondary physical user interface. While the LCD does include touchscreen capability, we intentionally added a 5-way navigation switch to provide redundancy in situations where a touchscreen might not be practical, such as when a user is wearing gloves or operating in wet conditions. We evaluated multiple input options, including the standard SPST push button. However, a single push button would require multiple components to achieve directional control, increasing panel space and wiring complexity. We ultimately selected the 1CW09136-11806 5-way navigation switch. It provides up, down, left, right, and center functionality in one compact PCB-mounted component, allowing full menu navigation while conserving board space. Its approximately 2.5 Newton actuation force provides clear tactical feedback suitable for field use. Each directional input is routed as an independent signal to the microcontroller, allowing for straightforward software integration. Although we're still waiting for the components to arrive, our code and testing strategy are already prepared for immediate validation upon delivery. Overall, this switch improves usability and system robustness by complementing the touchscreen interface. This slide shows the design of our user interface PCB. The purpose of this board is to consolidate all UI-related components, including the LCD and touchscreen interface, navigation switch inputs, and audio amplifier, into a single organized subsystem. This allows us to separate user interaction hardware from sensing and processing hardware. At the center of this design is the MAX 98357A Mono Class D amplifier, which interfaces with the ESP32 through I2S communication lines. Proper decoupling capacitors were implemented near the power pins, and speaker outputs are routed to the dedicated terminal blocks for clean external connections. The LCD interface header routes SPI communication lines, including MOSI, MISO, S-Clock, chip select, and control signals, to the microcontroller. The touchscreen interface is routed separately to minimize interference and maintain signal integrity. The 5-way navigational switch is connected through individual GPIO lines, allowing each direction input and center selection as a function of independent digital signals. Power distribution across the board is managed through regulated 3.3-volt rails with appropriate grounding considerations to reduce noise coupling between the amplifier and digital communication lines. As mentioned earlier, this board will be integrated into our stacked PCB architecture. The UI board will function as its own modular layer, allowing clean vertical integration within the enclosure while maintaining separation from radar and other sensitive subsystems. This slide showcases our full system enclosure design strategy. The enclosure model shown here was designed and rendered in Rhino 3D. This allowed us to precisely define board spacing, mounting locations, and external interface placement before moving on to the fabrication. The current prototype enclosure is being 3D printed right now at dimensions of approximately 10 by 8 inches with a depth of 2.3 inches. These dimensions were selected to accommodate our stacked PCB architecture while maintaining a compact, portable form. Internally, the design follows a stacked architecture, separating the UI, power, radar, and sensor subsystems into vertically organized layers. This improves organization, simplifies serviceability, and allows each subsystem to remain modular. Dedicating PCB mounting plates ensures mechanical stability and controlled board spacing. Once our final PCBs arrive, we'll install them into the prototype enclosure to verify fit and component placement. That physical validation step will inform final adjustments before we complete detailed features such as cable routing channels, integrated handles, ventilation slits, and sensor apertures. This staged approach ensures that mechanical decisions are informed by actual hardware dimensions rather than assumptions. The enclosure is being printed in PETG material. This was selected because it offers high impact resistance and durability compared to PLA, improved temperature resistance, and better layering adhesion. Since this device is intended for field deployment, material toughness and thermal stability were important considerations. PETG also provides sufficient structural strength while remaining relatively easy to print, making it a practical choice. Externally, the enclosure incorporates integrated side handles to support portability during operation. It's important to note that these handles were dimensioned with RF safety compliance in mind. At their furthest point, each handle must maintain a minimum distance of 20 centimeters away from the radar module. This ensures compliance with the FCC RF exposure regulation that we discussed earlier. This spacing ensures that normal user handling inherently maintains the required safe separation distance. Overall, the enclosure design supports modular stacking, mechanical durability, RF compliance, thermal management, and field-ready usability.
Here's an overview of our software selection. For our MCU, we had to decide between the ESP32, STM32, and Raspberry Pi. We preferred the ESP32's wireless connectivity over the STM32, in addition to a simpler development process. And we chose the ESP32 over the Raspberry Pi because we felt that the Raspberry Pi was overkill for what we were trying to accomplish. While we did have sensor fusion, we didn't need as much performance as the Raspberry Pi offered, and we preferred the lower complexity of working with the ESP32. In terms of choosing a specific ESP32 model, we chose the Room 32. We preferred the lower cost and the power draw that aligned best with the components that we were working with. And we didn't really require the higher cost and power from the ESP32S3. For choosing the Room 32 over the C6 room, we preferred having the dual core, which provided more processing headroom than the C6. And the mesh networking and Wi-Fi 6 that the C6 offered was not useful to us for our project. So our final choice was the ESP32 Room 32. Part of our project was building a smartphone app to accompany the device. So the next decision we had to make was choosing the communication protocol between the app and the device. We chose to go with Bluetooth Low Energy. The other options were Wi-Fi, MQTT, and USB, but the main considerations were between Bluetooth Low Energy and Wi-Fi. We ended up going with Bluetooth Low Energy because the lower bandwidth and the requirement of phone proximity best matched the use case that we were going for, and we preferred not to have to deal with the complexity of running a web server or connecting to it, or increased power demands from Wi-Fi. And the benefits of communicating in Wi-Fi in general didn't really apply to what we were going for, with a low proximity, high latency, and low bandwidth type of connection. In simple terms, our device will be collecting data from the radar, the infrared, and the INS to provide the user with location tracking on a map, a heat map representing heat signatures from the surroundings of the device, and most importantly, human detection markers representing potential humans detected based off their breathing and heartbeat data, and presenting these locations to the user. To go into more detail, the device will function in sessions where the sensors will be continuously sending data to the MCU. From there, our logic will come up with confidence scores based on how confident we are that a human has been detected, based on their signatures that have been picked up by the sensors. In addition, the user can also place their own markers on the map, keep track of where they've traversed, and any markers around them. Finally, they can record these sessions, record multiple sessions, look through history of previous detections, and any data that has been recorded in the past. Here is our use case diagram, which reiterates our functionality. We want the users to be able to create new sessions where they're traversing a location and searching for human markers. We want them to also see the raw data that's being transmitted from the sensors. And we also want them to be able to access data on a smartphone app, providing additional utility and convenience for first responders. Our flowchart goes into detail about our user interface. We're going to present them with three main views. The first view, which is raw data, which is very useful for debugging and confirming that the sensors are working and transmitting data correctly. The next view will be a coordinate map, where the user will see themselves on a bird's eye view on a grid, see where they first started traversing the location and where they currently are, and various markers around them that have either been placed by them or automatically detected. Finally, the user will also be able to see a heat map view, which will provide a color gradient from blue, which is very cold, to bright red and orange, representing high heat signatures detected around them, giving the user another layer of information to help their reconnaissance. So here are some sketches of our user interface. Regardless of the page that the user is on, they'll be able to see their session information, such as which session they're on, how long it's lasted, how much distance they've traveled in that time, and the total detections of humans, if any. On the left, you can see what our raw data view will look like. It will just be some basic text and graphics representing the data transmitted from the sensors, and it will be updating many times a minute to provide accurate and recent data. Below that is a sketch of our heat map. As you can see, it will offer a color gradient based on the heat signature data from the infrared sensor. And on the right, that will be our coordinate map. The user can see where they first started, their position relative to various markers around the map, representing human detections, and the user can also place their own markers, edit them, remove them, and cycle through them. In addition to our device, we will have a smartphone app providing another means of access to our device's data from the sensors from its surroundings. At the top, since it will connect to the device using Bluetooth Low Energy, will show the user the status of the connection. Below that, if there's a live session that's currently going on in the device, the user will be able to see all that data on the app as well. This includes the raw data, and the heat map and the coordinate map. So all these views will be able to be accessed through different tabs on this app. In addition, just like on the device, the user can access the history of previous sessions, previous detections, and the user can change the device settings through the app itself, such as radar sensitivity, connection latency, refresh timing, and so on.